Hi, in this class I'm going to talk about assessing assumptions of simple linear regression using plots and other information. This is chapter 14. Remember, we have some assumptions. Let me remind you about the assumptions we have. Here we have some assumptions about the simple linear regression, and I'm going to go over them. And let's start with the variance of the error term, which has to be the same for all values of the independent variable. Okay. So here's another definition, another discussion about that. What this is saying is that the variance of the error, how the error varies, has to be the same for all values of the independent variable. Here we have the independent variable, we have the model, that's our line, and we have the observed data. All this observed data generates error, residuals. So the distribution of these residuals have to be similar along all values of the student population. Let me show you that with this applet from MindTap. Again, here is the model, and here is the size of the residuals. Remember, I showed you this video. I showed you this chart in the previous video, the video before this, the first video about residual analysis. And this is the size of the residuals, negative residuals, positive residuals. And they have to be, in order for us to have constant variance of the error term, the error terms, they have to vary in a random way throughout all the values of the student population, which is the independent variable. So I cannot have small values of residuals here and big values of residuals here, because then the variance of residuals wouldn't be constant, and they have to be constant. Okay, that's what the assumption is. This is basically saying that our model predicts the sales in a similar way regardless of the size of student population. That's a very strong assumption. Okay, so this is what we're doing, and what we're looking for is a good pattern like this, which is like scattered around the zero line in a similar way. So low values of x, low values of x, high values of x, low values of x and high values of x, the variance of residuals, they vary in similar way. That's different than this case. In low values of x, the error terms, the residuals vary little. They don't vary much in low values of x. In higher values of x, the residuals vary much more, which means our model predicts very well low value when we are taking into account low values of the independent variable. But when we consider high values of the independent variable, then our model is not predicting well because we have too much error. This is non-constant variance. You can see that you have kind of a V, like a V here. So it's like this, and let me see, and like this. So the variance increases as I increase the value of x. In this case, what I'm looking for is kind of an ellipse, which shows that they vary all in the same way. Okay, so another problem is in this one. This one looks like a U. So for low and high values of x, we have only positive residuals, and in the middle we have negative values of residual, which is not good. So our model is not predicting well. So this is the concept of constant variance. Has to be like this, cannot be like this, cannot be like that. So how we do that in Excel? In Excel, I'm gonna skip these slides because they're just like telling you the same thing, and this slide is telling you how to do in Excel. And in Excel, what you're going to do is go to data analysis, regression, select regression, okay, and then you input the Y range, which is sales, our dependent variable. Our sales depends on the population of students, okay, and we click label because we have labels in the first row, and then we check these 3 boxes. We check residuals, check standardized residuals, and check residual plots, and click OK. Now you can see that you have the plot that I was talking about. Is the same plot that we have here on Mine tab. Okay, here's the plot, and it looks like we have kind of constant variance, the values. Maybe they are not too constant for middle values of x, but that's not too bad. Okay, and this judgment is more of visual judgment, so you have to look and see if the errors they have, the residuals they have the same size, they vary similarly along all values of x. Okay, also if you scroll down, you see that we have a new table here. We have a table with information about each one of the restaurants, which is called observation, and then we have the predicted sales, and we have the residuals, and we have the standardized residuals. This is a new one. The standard residuals is the residuals divided by the variability of these residuals. Okay, and we have that in the next slide. So standardized residuals are taking into account the variability given by this standard deviation of the residuals. So we get each residual and divide by the standard deviation. Okay, and this gives us the standardized residuals, which is given directly in Excel here. If there are too many decimal places, you can go up, click home, go here and reduce the size of the decimal places to make it more like easier to read. You can also centralize. I like to centralize. Okay, so here the residuals we have here are the same residuals I computed for you here. Okay, if you want to check later. And this is giving the standard residuals. We're going to judge the distribution of residuals not only using the residual plot, but also using the standardized residuals. Okay, the standardized residuals can give us tell us a different story, and if we plot them, okay, we can plot the standard residuals, and what we are looking for is that residuals that are between -2 and +2. These are the residuals that we are looking for. So I can plot, let's plot this. So if I select here, go insert, scatter. So these are the standard residuals. What we need is residuals between 2 and -2. So residuals cannot be, standard residuals cannot be higher than 2 and cannot be smaller than -2. Okay, this is what this slide is saying. All of the standardized residuals are between -2 and +2, indicating that there is no reason to question the assumption that the standard error has a normal distribution. So we are looking for residuals between this range. If we have residuals smaller than -2 or higher than 2, then we have problems of normal distribution. Okay, and also we have outliers. Outliers are observations that are higher than 2, in the standard residual is higher than 2, or the standard residual is smaller than 2. Smaller than -2. Then outliers, let me put here, outliers are observations whose standardized residuals are higher than 2, than the +2, or less than -2. Okay, and outliers affect the whole model when we have to get rid of these observations that have standard residuals higher or smaller than plus and -2. Okay, that's what we're talking about here. And also we can plot this, we plot it here, and this would be a good indication of normal distribution. But also we could get let's do that one more time. We could get the normal probability plot, which is here. I don't have to go over everything because everything is set up in the same way. The only thing that I'm doing that is different is I'm checking the normal probability plot. And here's the normal probability plot. And what we're looking for is a straight line, very similar to what we have here. And this tells us that the residuals are normally distributed, okay? So these are the steps you have to take in order to test these conditions of residual analysis. Let's see if we have one problem in MindTab so we can go over very quickly some of the questions we might have. So if you go here, residual analysis, validating models, let's click here, section 14.8, and then I click on applications. So we have all the discussion here. You can read, I suggest you to read, and then we have the data. So let X equal advertising expenditure and Y is equal revenue. So independent and dependent variable. Test whether revenue and advertising expenditure are related. So this is, remember, this is a test of significance. We have a specific video about that. So let me do that very quickly so you can see. If I copy. Okay, so let me do on this one because we have the data, cost of living. Okay, let me open this very quickly and let's see how it works. So we have different cities in the United States, and we have an index and a density. So let's see what the problem is talking about. Develop the estimated regression equation that can be used to predict the cost of living index. So this is a cost of living index. So this depends on the density. Cities that are more dense tend to have a higher cost of living, right? So New York, a lot of people living there, the index cost is very high. Same thing for San Francisco and so on. Okay, so that's, I'm gonna skip the statement. I'm gonna try to go here. So develop an estimated regression equation that can be used to predict the cost of living. So I'm going to do that by using the data analysis tool, regression, okay, Y range. Our dependent variable is the index cost of living, and my independent variable is the density. Okay, so density influences the cost of living. I have labels, new worksheet, residual. I'm going to skip this normal probability plot, and I'm going to click OK. So what we have to look here, we have lots of information. One of them is develop a regression equation. Okay, so this is develop an estimated regression equation. So to develop this regression, we would say something like the living cost is equal to my B0, 47.01.0, let's say 02, plus the coefficient 0.002 multiplied by the density. Okay, that's my regression equation, right? If I want to test if there is a significant relationship, to test the significance, test of significance. So my null hypothesis is that B1 is equal to 0. My alternative hypothesis is that B1, let's say, is different than 0. Okay? So where is my test of significance? Is given by this t statistic. This t statistic is very high, and then I have to look at the p-value. The p-value is very small. I can turn that into a number, and I see that this is smaller than 0.05. And now I check the residuals. So the residual plot doesn't look like we have constant variance because we have residuals that are much higher here. At the same time, if I scroll down and I use the standardized residuals, I can see that some of the residuals are higher than 3 and smaller than -3. So let me reduce the number of decimal places. This one is too big, right? And that's it. Like this is how we analyze some of this information.